So I can probably start now with introductions, and then by the time we get the presentation going, we'll have a few more people here. But thanks everyone for coming to this IBPSA Mixa. This particular topic, so this IBPSA Mixa is sponsored by, or not sponsored by, but organized by the Architectural Simulation Subcommittee under IBPSA USA's Research Committee. And this is our third or fourth one, so we're trying different times and different topics. So any feedback you have afterwards is great for us to hear for planning for future ones. Today, Lisa Ng is going to present a short presentation to us on infiltration. She is a mechanical engineer at NIST, the National Institute of Standards and Technology, and she has expertise in airflow modeling as well as contaminant energy modeling, and I know I'm forgetting something else that I meant to say. Sorry for my lack of preparation. Indoor air quality, that's always an important one. So Lisa's going to give, roughly maybe a 15-minute presentation. If someone has questions during that, just raise your hands or leave a message in the chat. But if there are questions that don't come up during the presentation, we'll have, like I said, a lot of time afterwards just to have questions and for other people to give their views on infiltration kind of in a more casual exchange. And so at that point, people can kind of unmute themselves and talk as long as we're not, if people start talking on top of each other, we can start doing the hand raising, but we'll see how that goes afterwards. So at this point, I'll hand it off to Lisa. Thanks for agreeing to present this. It's a really exciting topic. And I did also forget to mention Lisa, in addition to being an ASHRAE member, is also an IBPSA USA member and serves on the Architectural Simulation Subcommittee. So thanks, Lisa.
All right, well, thank you so much for the introduction, David, and thank you to the subcommittee for inviting me to give this talk. Today is going to be really informal because it's supposed to be a happy hour, a mixa, as we have called it. And so please feel free to put your questions in the chat or raise your hand or unmute yourself and ask if you have a burning question that you don't want to wait until the end. But it is an open discussion, so it's not going to be technical. So let me begin by sharing my presentation. All right, so today's presentation is titled Infiltration, the Good, the Bad, and the Ugly. So I'd like to cover these subtopics within this big topic of infiltration. Again, my name is Lisa Ng. I'm a mechanical engineer. My expertise is in indoor air quality, airflow, and contaminant simulation, as well as a little bit of energy modeling on the side. I'm a member of IBPSA USA, as David mentioned, as well as ASHRAE. And also I serve as a mentor in many capacities. You'll see a lot of student work featured in my presentation. We've worked with co-op students to help us develop some of these tools and products. So I definitely thank all of them. And some of them are in the audience. So thank you for being here. All right. All right, so the good thing about infiltration is that we're talking about it. Let's go on to the bad. Just kidding. Let's go back to the good. There are some good things happening within the world of infiltration. And one of the things is a video that was produced by a student of ours from Drexel University. I don't know if she's on today, but her name is Jortiana. So the presentation will be available afterward, and that hyperlink is available. But it is a pretty introductory video into how building physics works and talks a lot about infiltration and the factors that affect it. And we think it's a really great way to get an intro into the subject without all the equations and all the math that is involved. So I definitely encourage you all to check that out to get a 101, but today we're going to talk a little bit about that 101 as well. So to begin, I have 2 trivia questions. So I would love for you to open up the chat. I don't know if I can find the chat, but open up the chat and tell me, or tell everyone if you're comfortable, which direction does air flow? Is it A, from high to low temperature, or B, from low to high temperature? And then the second question is, can air infiltrate buildings that are pressurized? The answers are yes, no, or C, it depends. So take the next 30 seconds and put in the chat what you think the answers to those questions are. And I might not be able to get, oh, I do get to the chat, great. All right, so one person has answered 2, is yes, air can infiltrate buildings that are pressurized. Anyone else? Okay, 1C. Oh, the C one is yes, it depends. Matthew says depends on pressure, local pressure gradients. Alfonso said 1 is A and 2 is C. Amir says 2 is yes. And then IBPSA USA, our host today, says temperature goes from high to low. Oh, airflow goes from high to low. All right, so I think we have a mix of answers here. And if my answers are wrong, I am sorry they are wrong. This is just how my brain works. All right, so Matthew says the first one is A, and then number 2, the answer is C. So I think a lot of you got the answer to number 2 correct, which is yes, buildings that are pressurized can still have infiltration, but the answer is also C, it depends, because it depends on the weather outside, what's happening in the building, as well as where in the building there is pressurization. It is oftentimes hard to pressurize an entire building unless you are doing a building pressurization test. And I have some screenshots from the introduction to building airflow physics here on screen, because it does go through the answers to the questions. Now, for the number 1 question, which direction does air flow? Some people said A and some people said B, because, you know, A, let's see, what did I highlight here? All right, so I said that the air flows from low temperature to high temperature, meaning that if it's cold outside, then the air is going to want to come in, which is counterintuitive to which way temperature flows, which is from a low temperature. Well, actually, no, it relates to how temperature goes, which is from low temperature to high temperature. So that can be a little counterintuitive, but the graph, maybe on the graphic on the right, shows that, you know, if it's cold outside, the air is going to enter the building because it is cold outside, and then it's warmer. And then as the temperature decreases or increases as you go up, there's more and more airflow that goes through the top of the building. All right, so hopefully that made sense. Now here's 2 more questions that are also answered by our introductory video. So 3 is, what climate is infiltration an important issue? Is it cold, hot, or depends? And then number 4 is infiltration a constant value? Answers are A or B. So go ahead, take the next 30 seconds and put them in the chat. So Matthew says C and B are the right answers. Anyone else? All right, we got 3 as C, good. C and B. Oh, I think these 2 questions you all know. And then Andrew says 3 all climates, and then I missed the second part of his. But people are saying 4A, 4 false, CB, CB, excellent. All right, so I'm glad that these 2 questions are questions that people understand already, which is that climate is going to be important in all types of climates, and really where it depends. Matthew says not in Hawaii, because it's so nice in Hawaii. Why would you care about infiltration? You want that those mild and beach-driven wind to infiltrate your buildings. And then number 4, infiltration is not a constant value, which I'm so glad to see that people understand. It's definitely affected by weather, HVAC operation, and the video, like I said, will show more of that in an animated form. So thank you all for the participation. Hopefully you can come up with some questions for discussion later. So infiltration, the good about it is that, like I said, we were talking about it. Many of you know more about infiltration than maybe you thought you did. You understand the concepts, and that's great. So what we can do about infiltration is we can reduce it, because there are better and better technologies to improve building envelope air tightness. And then there's also a lot of mechanical ventilation solutions to bring in outdoor air, despite it not coming in through the cracks around your doors and around your windows. What's also great are that there are many tools to help us model infiltration. So that's a plug for the work that NIST has done. We've worked with Oak Ridge National Laboratory, as well as the Air Barrier Association of America. But before I want to get to the tools, I do want to touch on the other 2 aspects of the tagline, which were the bad and then the ugly. So the bad. Here are some questions that people have asked me in the past when I've given presentations like this. And the questions are, how leaky is my building? How do I know what it is? Does infiltration even matter? And then how do I model it if I do care about it? How do I model it in an energy model? So I don't know if anyone wants to speak up now and tell us about any of these topics that they've encountered or put it in the chat, you're welcome to do so. Okay, Amir, he says to do a blower test. That's right. That's definitely one way to tell how leaky your building is. But how do you relate blower door test to infiltration? Is it the same? Is it the same amount? All right, Andy says, don't divide by 20. He doesn't like that his name is attached to n divided by 20 all these years. Maybe Andy, if you're not being shy, you could unmute and tell us a little bit why we don't just divide by 20.
I'm unmuting. Can you hear me, Lisa?
Yes, we can hear you. Thanks, Andy.
I was being somewhat facetious, divide by 20 is a rule of thumb for residential blower door results. Rules of thumb are great, but if you really want to know what the rate is a function of weather conditions and all the details, you got to use models and physics and and all that. Rules of thumb are great, but sometimes those thumbs end up in your eye, right?
That's right. Thank
They're
you.
in my teeth.
Yes, you did. Yes, you did. So Al put in the chat the flow coefficient model, which is one of the models that you can use to model infiltration. There are several. Something that I'll say about these coefficient models, and Andy, Steve, Emmerich can correct me if I'm wrong, but they were also developed for residential buildings, so they may not be applicable to larger commercial buildings. And then Heba says infiltration matters in air-conditioned buildings more than non-conditioned buildings. Heba, do you want to unmute and tell us more about that?
Hi, Lisa.
Hello.
I think that the infiltration is a bugaboo of the air-conditioned buildings because it increases the working of the air condition. It is like if I make the building conditioned, it takes the air condition outside. It works as minus of the air condition. But the non-conditioned buildings, it's already has action and reaction with the outer environment. So it's already contacted with the outer environment. So I think the infiltration matters more in the air conditioned. We should control the size of the condition. That's all.
All right, thank you so much. So you're saying that infiltration may be detrimental if not controlled for air-conditioned buildings, whereas non-conditioned buildings, those that rely on natural ventilation or a sort of mixed mode model, may incorporate outdoor air already. So it's not as much of a concern because it is already being utilized. Yeah, that's a great point. I definitely am talking about conditioned buildings since much of the US has buildings that are mechanically ventilated. So Al, did you want to come off of mute to tell us more about the flow coefficient model and what kind of buildings you use that for?
Yeah, you can hear me?
Yes, we can hear you.
Yeah, so I'm at FIAS, formerly the Passive House Institute US. So anybody who's familiar with passive building knows we're a little nuts about infiltration. And most of our stuff, we end up using a monthly model that sort of follows that divide by 20 rule of thumb. But recently we've been doing a lot of research into thermal resilience. So in Energy Plus, I've read Lisa's paper on the commercial flow and for one of the other models in there, and then ended up going down a rabbit hole and figuring out that the flow coefficient model works best with the data we have available, which are those blower door numbers that are fairly easy to convert. And then that helps us get that dynamic infiltration dialed in so we can make smart decisions about the building envelope when we're trying to plan for thermal resilience. So that's where we've been using it here.
Excellent. Thank you so much, Al. I love to hear that things that we're doing at NIST are having real world implications. And that's exactly where I would like to see the commercial building industry go as well, is to take into account building airflow physics so that they can make better informed decisions about things like air tightening or energy upgrades. Thank you so much. All right, so Matthew, you put into the chat per energy code for comparative energy modeling. Would you mind coming off mute and telling us more about that?
Sure, can you hear me?
Yes, we can hear you.
Yeah, my background's mostly in comparative energy modeling, so somewhat fictitiously modeling. It's not predictive modeling. Maybe the building hasn't been built yet, so you're just trying to comply with a local code or a third-party certifications such as LEED. So oftentimes the AHJ, the authority having jurisdiction, has an energy code that usually prescribes how infiltration is modeled. Typically the same in the baseline model as the proposed model. So
okay,
much more important in predictive energy modeling.
All right, well, thank you so much, Matthew. Yes, I completely agree with you in terms of like, let's for instance 90.1 standard. There's in Appendix G a way to, I'll say, account for infiltration. I won't say model, but account for infiltration, and it is the same between your base model and your improved model, which is interesting because what if your improved model has a tighter envelope? Why are we using the same infiltration? And so, I'll point you all to a paper I wrote in 2018 looking at the effects of using what I'll show you later to incorporate HVAC and weather into the simulations. And we showed that building envelope air tightness has a better energy savings when you use building airflow physics rather than the same value for both buildings. But let's move on and appreciate everyone coming off of mute. I didn't call on Steve Emmerich and William Doles because I work with them and they didn't ask a question. All right, so I'm gonna keep going. All right, so the ugly, and it doesn't seem like anyone here is subscribed to this, but I've definitely heard these in my tour of giving these kinds of talks, is that people might assume zero or constant infiltration. Zero infiltration would be for a very tight building, but oftentimes we're not modeling very tight buildings. And constant infiltration, like I said, doesn't take into account weather. So if you're in Alaska and you're looking at building envelope air tightness, energy saving, that's going to be different because different than in a city that is warmer. Another one is not taking into account HVAC operation. You'll see from that video that I linked up earlier that it's going to really depend on what parts of the building are pressurized or oversupplied, whereas other building locations are under pressurized or depressurized because of exhaust fans or other things happening in the building. And then not using the available tools. So I am going to use this time to plug the tools that NIST has. Why use a hammer when you can use a jackhammer? So these are the tools that we've developed, and we are always wanting to improve them in terms of how we can use them, how you can use them. And like Matthew said earlier, I am also a theoretical modeler. I use the DOE prototype buildings for these tools. And so these aren't real buildings, but I hope that they can be translated into real world implications. So like I said earlier, the tools that we've developed, we've done them with Oak Ridge National Laboratory, as well as the Air Barrier Association of America. We either use a combination of Energy Plus and CONTAM. Energy Plus, I'm pretty sure you're familiar with. Energy Plus is the building energy simulation from DOE, and then CONTAM is a software developed at NIST by William Doles, one of the developers. William Doles on the call. So if you have any CONTAM questions for him, now's the time to ask. But CONTAM is an airflow and contaminant simulation program. The two can be coupled, but we have not used the coupled version of any buildings for these tools. We've used a combination of both together or just separately. So the first one is called the infiltration calculator. Again, the slides will be posted later and these hyperlinks are active, but it goes to the air infiltration calculator. that is hosted on the Oak Ridge website. And what you can do is you can use drop-down menus to choose the type of building that you want to evaluate the savings from air tightening. So, excuse me. So we have used the DOE reference buildings. I think there's 5 or 6 and 1 residential building on this site. You can choose a type of building that matches the closest to what you have, or something that you're thinking about. And then you can input the size of the building, also choose the base leakage rate, and also the improved leakage rate, put in an energy rate cost and a gas cost. And what the infiltration calculator does is taking a database of simulation results that we've already pre-processed and scale them to the size of the building that you have input. And it'll give you your energy savings in terms of electricity, gas, and also how much moisture transfer may be saved through air tightening. And this will be especially important in humid climates such as those in the South. And so these are based on over 50 cities in the United States, some in Canada, some in China as well. And they cover most of the climate zones that ASHRAE defines, except climate zone 0, which is the coldest one. Okay. Another tool that we have developed in conjunction with Air Barrier Association of America is how to use the correlations that NIST has developed. So NIST, what we did is we took the contam models of the DOE reference buildings, and we correlated the infiltration to the temperature, to the wind speed, and also by whether or not the system was on or off. And we published this beautiful report as well as article, but that can be a lot to digest. And Air Barrier Association America really believe that our tool should be more available. So what they did is they sponsored us to write a written tutorial as well as do a video tutorial on how to do that step by step, how to get that work into Energy Plus. And I'll thank Ethan Yen, who's on the line. He's the student who helped create this video, so thank you to him. And so that hopefully gets the research into the hands of the people who are using these correlations. So all these links, again, will be live in the presentation later, but there's a video tutorial, there's a written tutorial, and then the last link down there is a link to an Excel sheet. So if you know how to use the Energy Plus zone infiltration design object, then you can input these A, B, C, D coefficients as I've linked up there in the equation at the top. So with that, that is my presentation. Again, it wasn't meant to be highly technical. I didn't want to go over how we developed the correlations, but I did wanted to use this as a time to open up for questions and discussion about all things infiltration. So let me stop sharing my screen here. Feel free to come off of mute or come off of a blank screen if you want. But I will answer the first question that's in the chat. What is the term? Why is the term infiltration used and exfiltration ignored? If it is intended to be interchangeable, why not use air leakage or air leakage rate? So that's a really great question. I've also had trouble kind of understanding when to use each one, and the combination of the two happen in a building. So where air is coming in, there's also going to be another part of the building where air is leaving, or exfiltration. And in Energy Plus, if there is air leaving the building envelope, because there's no energy penalty with that, they will say that flow is 0. So you're only having air coming in the building. Whereas contam, which is an airflow model, we accounted for air going in and out of the building. And so there's a net infiltration coming in. And we've tried to capture that with the correlations with the equation to say that even though there is air leaving the building at certain points, we did have to take it from a whole building perspective, because Energy Plus only accounts for infiltration and not air leaving the building. So I'm gonna ask Stuart to come off mute if you would, and help just to answer that question even further in terms of infiltration, exfiltration. What does it all mean? Should we even care if we only say infiltration?
Great, thanks, Lisa. I have 2 minutes. I got to get to another meeting, but
Okay.
there's actually, I wrote a paper or presented it in the previous building performance or building physics conference. You can look on the NIST website, and it talks about how Energy Plus and Contam address infiltration, and we use coupled Energy Plus Contam, and I kind of talk about the pros and cons of using the two tools, and that issue is addressed in there. So you can kind of read about air will flow in the bottom of a building and out the top when there's stack effect in the wintertime. And so that can have ramifications with contaminant dilution. So for your energy modelers, it may not matter so much. Sorry to say that, but if you really care about pollutants and contaminant transport, it matters more. So I'll try to put a link to that paper in the chat, and you can kind of read a little bit more about that.
All right, thank you so much.
Sure.
So let me go back to who asked it. So Michael, did we answer your question? Okay, you can flag us again if we did not. So the next question is, do we have an open studio measure that applies our research or what is done in the Energy Plus tutorials? That's a really great question, Luis. We did have an open studio measure, but then things got transferred to a different database or something, computer things that I didn't quite understand. So it is not currently on the building component library, but we will be working to try to get it back on there, because yes, it did incorporate all the values in the Excel sheet into an open studio measure. And what you as a user would do is select the building that either matches your building or most likely matches it. You would select a HVAC operation schedule, put in the envelope air tightness, and then it would do all the calculations for you. So unfortunately, it's not currently there, but we'll try to get it back onto the BCL website. Matthew says unconditioned air is more problematic than conditioned air leaving. Okay, see mold and conditioned buildings in hot, humid climates. Exactly, Matthew. So the air infiltration tool that was hosted on the Oak Ridge National Laboratory website, they added the infiltrate of the moisture part to it, because you might be able to observe from that tool that in, let's say, Florida, infiltration air tightening is not going to be a huge energy savings, but it will save a lot of moisture. And that's exactly what Matthew is saying there. So yes, it's not just energy, it's not just whether it's hot or cold, but how much moisture is in that air as it comes through. Energy Plus, you can model contaminants, but Contam also does this with much more flexibility in terms of, what kind of contaminants, when it comes in, when it's generated. And because infiltration into a building is not filtered, then you also may need to think about contaminants coming in through infiltration. All right. Yes. So David just responded to Luis's question. I hope I'm pronouncing that right, about the BCL, and we will try to get it back on there if we can. Yi Yun asks, are there easier low-cost ways to measure infiltration beyond the blower door test? So there is a lot of research in this area. There's people doing like pulse tests where they can do infiltration measurements using sound and other things. So there is research in the area. We personally internally have looked at thermal imaging and how we can relate thermal images to envelope air tightness, but it is an emerging field of research. So currently I don't have any lower cost ways to measure infiltration. Does anyone else have a solution or one that they've used successfully? Oh, Matthew did respond to that question. Oh, actually, Matthew responded to Luis' question about there will be one written by Lisa on BCL 1.0, but looks like it might be missing in BCL 2.0. Yes, that's right. There definitely was one on building BCL 1.0. My link to that one doesn't work anymore. All right, well, if anyone has any methods for testing infiltration that is lower cost than, say, blower door, please put that in the chat. I also want to delineate infiltration versus blower door. So blower door tests give you how tight that building is. It's a characteristic of the building. It shouldn't change a lot over time. It changes because maybe the building components deteriorate, ceilings deteriorate, but it is the characteristics of the building, whereas infiltration is this dynamic airflow through the building envelope that will continue to change. So a blower door number will give you an air tightness number. We can put that into Contam. Contam then calculates the pressure differences across all those different surfaces to determine the infiltration rate. All right, any reason, David asked, any reason why Energy Plus only considers infiltration and not exfiltration? So my theory is that infiltration is an energy impact, whereas air leaving the building is not an impact. That's why. But I was not there when Energy Plus was created. So I haven't been able to find out why they chose it this way. But if anyone knows, feel free to raise your hand or unmute or put it in the chat. Okay, someone says, Jung Hyun says that my measure may be in archive after a BC update, so I'll look into that as well. All right, and then my group leader, Steve Emmerich, wants to chime in, but can't currently, but he says hello. All right, and Stuart put the link to his article in the chat. And yes, thank you, Louise, for the support. That'll make us more motivated to get it onto BCL 2.0. And then David says, I want to do a time-lapse thermal image with dynamic state to look at envelope response. Yeah, that, I mean, to me, my theory was that we could use big data, you know, artificial intelligence, some sort of data mining tool to look at images versus blower door test results. And then you could correlate the two, but you would need a lot of data to build up that database in terms of a lot of blower door tests and a lot of thermal images. Okay, Amir wanted to ask why infiltration is not an energy penalty. So in terms of energy penalty, I'm talking that like when cold, let's say when cold air enters a warm building, there's an energy penalty associated with that. So Energy Plus wants to know how much cold air is coming in. But if warm air from the building is leaving, then to them, it's already been conditioned. Leaving the building is not an energy penalty. And so thermally, it's not an energy penalty. Now they might have to make up that air, and that's like a fan energy penalty, but a thermal penalty is not considered. All right, Heba wants to know, how can we make weighing between the low infiltration, which causes overheating, and the high infiltration, which consumes a lot of air conditioning? So how can we balance, how much infiltration we allow into our buildings when low infiltration may cause overheating and high infiltration causes a lot of air conditioning required, like in a warm climate. And so I always think of infiltration as something that is not controlled. So you don't know how much of it is coming in at any time of the year. And so because you can't control it, you can't depend on it, you can't filter it. So you can't control the contaminants that are coming in. You can't control the contaminants that are coming in. You can't remove the contaminants from the air. And then it's also unreliable, like I said earlier, because you just don't know. So if you are relying on infiltration as your outdoor air ventilation, then it's not controlled, it's not reliable, and it's not filtered. And so that's one reason why we would like to have a control over how much outdoor air is coming into our buildings through mechanical ventilation rather than through the cracks in our wall. And I will also say to Heba, if it's a naturally ventilated building, that's a whole different kind of system than a fully mechanically ventilated system. So that's something that I would say, talk with a design engineer, perhaps utilize some of our tools to figure out, is it worth it to increase building envelope air tightness because you save on all these other areas, whether it be moisture or contaminant control.
Hello, I do have a question. This is Alfonso Hernandez with Gensler. Whenever we are talking about energy efficiency, then the intuition is to lower infiltration, right? Mm-hmm. But if we want to, expand the horizons and include issues like, say, resilience, mm-hmm. Then we start seeing that maybe in areas that are prone to hurricanes, having a super insulated building, or not super insulated, super airtight building is probably not that good, because those constructions actually will tend to blow, with an increased pressure on the envelope itself. So I was wondering if there was some sort of study somewhere that also would take into consideration like high wind force.
Yeah, thank you so much for your question.
Yeah.
excuse me, so I don't have any experience designing buildings in that area. So if anyone does, please put that in the chat, as well as my NIST colleagues who may know more about this. But my initial reaction is that when we're talking about resilient buildings, it's not just to survive acts of climate or weather, but it's also the resilient of the building itself, in terms of if you do allow a lot of infiltration into the building because you want it to withstand stronger winds, then does that mean that building materials inside are degraded over time, whether, and mostly from moisture, degraded from moisture, and also moisture coming in to cold buildings also has moisture implications. So not just the moisture in the air, but the moisture condensing on surfaces that you may or may not see. So I think there's a holistic simulation of buildings that needs to be done when talking about that is not as straightforward as if we allow a building to be more leaky, it may withstand higher wind, which I don't know if that is true because that's not my expertise. So I'll leave it to the experts to answer, but that there are other implications with infiltration that may not be as obvious outright. But thank you. It is a very important topic to consider when we are looking at our current, climate, literal climate weather. And then I'll also point out, maybe Steve can give us a link, but there are publications that NIST has done which looks at energy savings for retrofitting in many different kinds of buildings. Okay, and David says, prior to recent Marshall fires, I didn't think of infiltration as a fire safety issue, but that came up as possible issues, even for ash damage to buildings not directly in fire zone. And for those not in Colorado, this was the recent fires in the Boulder area. So David, could you unmute and talk more? So I understand the ash damage, but can you talk about infiltration as a fire safety issue?
Yeah, so because we had sustained winds, like 100 mile an hour, so it was hurricane force winds. There was thought that embers were being driven in kind of through the envelope into like the framework of the building. So like I was thinking if you had like hardy plank or some sort of non-combustible exterior material, you'd be fine. But it seems like sometimes even like furniture inside like might have started burning before the envelope itself was, or components inside the envelope, which isn't something I had thought of. And again, I don't know that this has been tested and confirmed, but it was something that I had seen some people, saying is a possible condition that happened.
All right, thank you, David. Yes, and then Steve, you're only sending messages to me in case you didn't know, but he says it's also a major issue for wildfire smoke, which is kind of related to the ash in terms of it coming through buildings that are not as tight. And yes, can have implications, like David said, for those not even directly in the fire zone. Any more questions or topics of discussion related to infiltration?
So I have one. I know moisture, right, in buildings is in humid climates is often a problem, and Energy Plus doesn't necessarily do a great job, like something like Wolfie or other tools. And are there ways to take some of the outputs from NIST tools to feed into other tools that do hydrothermal analysis of the envelope?
Yes, so thank you for the question, David. So we do have another tool called Contam Results Export Tool, which is a web-based tool where you do the simulation locally, and then you select your project file, your sim file on there, and it'll output a schedule of infiltration, which is normalized by the surface area, exterior surface area. And so you can put that schedule directly into Energy Plus, or you can take those units that it comes out and convert it to whatever units that your tool might need. But you would have to assume how much water is in that air. And so you would have to combine it with, let's say, your dry bulb, your wet bulb, your humidity outside to determine how much water content is in there in order to do that kind of modeling.
Thanks.
Okay, so Lee says, great presentation. Thank you very much. Yes, there's some questions about where the infiltration retrofit paper is. Steve Emmerich just put one of the simulation papers that for the retrofitting. But if you Google NIST multi-zone modeling website, we do have a list of relevant case studies / papers that talk a lot about this stuff, as well as list the articles that we mentioned. So please search there, or you can join my listserv. You send an email to infiltration plus subscribe at list.nist.gov, and we try to push out new publications, things like that for our community who's interested about infiltration to be abreast of. Okay, Matthew said, interesting idea. I think the small embers would have burned down more quickly with high winds, whereas larger burning material would not. Regardless, direct flames were probably more destructive. Yeah. And then, yeah, you're welcome, Luis. Oh, can I drop the list email in the chat? Yes, I can. So give me 1 second. I'll also put all my other contact information there too. Okay, let's see. And Matthew said on wildflowers, he also lists another paper by Joe Streebrick. And he talks about and then also the urban wildland interface ICC code covers this. But for whatever reason, Boulder County isn't requiring rebuilt buildings that burned down in the recent fires to follow this code. Yeah. I'm in Gaithersburg, so I don't know. We do have a campus. This does have a campus in Boulder. Anything else? David, I see you on screen, but I don't see you or hear you. I didn't know if you were talking.
Oh, no, I had my screen off. It might have been frozen on yours, but
Okay.
I wasn't asking anything.
Okay.
But yeah, if anyone has any topics related to this, this is a chance. You got a lot of experts on the call to give feedback to any questions or thoughts.
Yeah, I will answer a question that actually Nicole asked me yesterday in terms of the type passive house requirements, which last I looked, correct me if I'm wrong, were 0.6 air changes at 50 Pascal, and the use of double hung windows. I will say that we have a net zero test house on campus. It does have double hung windows, and its building envelope air tightness hovers around 0.63 air changes at 50 Pascals. So I don't know if we would pass passive house, but I suppose with better technology, our house was built in 2010, it was completed in 2013. Window technology has gotten better, so perhaps we could get to 0.6 air changes these days.
Yeah, thanks, Lisa. I was curious if others know as well. I know Al's on the call, maybe he knows, but we've been having trouble with some clients that want to use double hung or single hung windows, and we just know they're incredibly leaky. But then when we get the test data for them, they show up as actually really good, and then we don't know what to do with that. So just curious if people have ideas on that, or if you have blower door tests from projects that have double or single hung windows.
Is it because when you test a component, it can be very good, but when you put it all together with the joints and the everything else, that's where
that's what I was wondering. Yeah.
Lose it. But yeah, our net zero house 0.63. I don't know if that would pass. I don't know if you round down or
yeah. So for passive house, it's 0.06 CFM per square foot. I always forget what the ACH would be for that. But yeah.
It depends on the building size, right?
Yeah. So square foot of floor
envelope area.
Oh, envelope area. Okay.
Yeah, 0.06 CFM at 50 pascals. If it's taller than 5 stories and non-combustible construction, it will allow for 0.08. And a lot of that's like we had mentioned earlier in the call, people have been talking about the durability of the airtight buildings and trying to prevent moisture from damaging the materials in the wall. So that's where a lot of that backstops too. in terms of double hungs, sorry to take over your question
No,
here.
yes,
Uh,
please.
but like in terms of double hungs, right, unless you're seeking out specifically airtight double hungs where they get a lot of compression on that gasket between the two sashes, it's not going to hit that same kind of performance that you get with a tilt and turn where that entire gasket around the whole window is compressed. So any projects, nobody seems to pick double hungs these days for their like natural ventilation capability where you pull one sash half up and pull the top sash half down and get that convective loop, but they want the look. And so what we see a lot of times with that is people going with tilt and turn windows that have a simulated double hung style frame across the middle of it. So it looks like a double hung. The Historical Society won't yell at you too much, but it's a more modern, properly gasketed window.
Yeah, we've been recommending those recently, but then we still find people want the regular, and yeah, the test reports seem good, but we know in reality it won't be. So we've been trying to steer them away, but yeah, no, it's some great points. Thanks.
Yeah, and the only other justification I could see for double hung, which is also speak about an infiltration nightmare, is if you wanted to allow occupants to put in like window shakers or something for cooling instead of a centralized cooling system. But that's a whole nother can of worms that, especially from an infiltration perspective, I would try and avoid.
Yeah,
there is an ASTM 783 standard for testing air leakage and fenestrations. And there are a number of vendors that provide that service. So depending on where you're located, you could have those field tested. And the manufacturer should have specifications on their results. They're also required to do that for AAMA.
Yeah, I got results for ASTM E283, I think. Can't remember the number for the air infiltration. And I got some for double hung, not simulated, but regular double hung. And I got some for tilt and turn, and they were about the same. I was shocked. I don't know, but I see Richard's comment that, the tested components are always going to be way different. Yeah, so 283. Yeah.
While we're on the topic of passive house, can someone try to defend to me why we should be using the same standard for coastal Southern California and Minnesota?
In terms of infiltration numbers?
Yeah.
It's that the prescriptive backstop requirements, and it's just really driven by that envelope durability. And in the winter, and especially in like the cooler climates, you tend to get a lot more in energy savings, like that cold air coming into the house type of infiltration. So that's our justification why we keep the same infiltration requirement across the climate zones. The targets we change, right, for insulation and stuff, but in terms of infiltration, it's a do not cross line for at least for what we do.
Right, but for like, I don't see a reason why it would be that strict in like coastal Southern California, even on a durability basis. It's dry and it's never gets colder than 45 or hotter than 85 Fahrenheit. So I'm not sure how that's a significant durability concern. I understand it for Minnesota. It makes sense there. I don't get it for Los Angeles. I don't know why you build a building that tight, especially if it's much more expensive to do so.
Well, and I think part of the reason too that we, at least from like where our targets and our standards have come from out of like BOPT optimization, is the model almost always picked a tighter envelope because air sealing traditionally has been a lot cheaper to get a good blower door number than it has been to add an extra couple inches of foam or spec like high grade European windows. I could look a little bit too into like, because like you said too, we are less concerned about durability in those climates. Our hygrothermal requirements tend to be a little bit less because we're not super concerned about condensation in the wall assembly. But from what we've seen too, not like having a leakier envelope helps a little bit, like has been said before, in some of those hot climates. If you're not going to provide any space conditioning, the building will float a little bit better with the outside temperatures. But anytime that it's cold or anytime that the wind blows from a direction where you don't want it, or you don't want that quality of air coming into the space, like it's your indoor environmental quality is much more controlled than if it was leaky.
When you use the Air Barrier Association tool that's in concert with NIST, you will see in southern climates that the moisture gain can be pretty significant, even though your energy gain is not. So durability is a major control issue, or air tightness is a major durability issue in the Southeast and even in Texas.
Yeah, I get the Southeast. I get cold climates. I don't get Southwestern climates. Right. Yeah. Anyways, I'm not sure we're going to resolve that on this call.
No, I appreciate you raising the concern though, and I will investigate this a little bit more because it's piqued my interest and it's part of what I'm working on right now. So
Yeah,
I
one of the
appreciate the
papers.
question.
Okay, so one of the papers that we wrote, I mean, climate zones in California, I know they're vastly different than, there's just a lot of climate zones in California. So in terms of the paper that we wrote, we looked at the 8 climate zones defined by ASHRAE, and we found that using like just a wind-driven infiltration relationship, which is in those DOE buildings versus the one where we take into account temperature, wind, as well as HVAC operation, we do find that the tighter buildings in these warmer climates will actually use more energy because they're not as leaky. They will need more air conditioning. And when they need gas, they might even need more gas. So it does show that there will be more energy implications for these warmer climates that may have relied on this cooler air for, free cooling. But I will second the contaminant issue. You said did you say Los Angeles earlier? Matthew?
Yeah, Los Angeles is a good example, but
Yeah,
pretty much anywhere in SoCal.
So let's say the air pollution that may be in Los Angeles, if your building is leakier, you may be bringing in those contaminants to your buildings, whereas if they were coming in mechanically, then you can filter them out. And moisture may not be a huge issue, like you said, but I will echo, I think it was Al who said, or someone said that, yes, the air infiltration calculator on Oak Ridge website will talk a lot about moisture, and even if it's fairly dry air, you may still get moisture that is condensing on places such as in between the walls, inside and outside wall that you may not see, and those are things that need to be considered. But again, I'll let the standards experts and Passive House address your concerns officially.
I guess another question, Stephen posted that paper in the chat, but it's on the ASTM site and that's a paywall. Is there another way to access it?
If you search the title of that, it should be available on the NIST website. Since we are federal government employees, all the work that we publish is also published for free, but in an unformatted way. So let me see if I can find it for you.
Great, thanks.
And if I cannot, I will find out why we have not posted it to our website. So let me write that down. All right, so Steve has also volunteered that if you send me or him an email, you can send me an email. He'll gladly share the PDF with you.
Okay, thanks.
All right, do we have any other topics or questions for infiltration?
I guess another one I can ask. I know that there were some studies, at least on the residential side, that were looking at sort of where infiltration occurs and sort of priority areas. And I'm not sure how much the modeling actually sort of captures those explicitly in the models. So looking at band joists, looking at top plates, things like that. And on the commercial side, I haven't seen anything like that. I imagine there's probably quite a lot of details that account for most of the infiltration. And it matters also where those holes are with the neutral pressure plane. So I'm curious if sort of any study like that has been done on commercial buildings and across a range of commercial buildings. So anything from like offices were relatively small zones to something like large retail stores where it's just one big area.
Yeah, that's a really great question in terms of building components and where. When you said where, I thought you meant where, like which part of the building, not which component. So I personally have not seen it done by a component saying like around the windows, around the doors is the most important. So I haven't, but anyone else has, please put that in the chat. And then David, the link that you put, yes, is to the weather correlations paper. But Matthew and others had a question about the ASTM paper, which is simulation analysis of potential energy savings for air sealing retrofits of US commercial buildings. So that one, we could not find a public version of it just yet. Oh, and then Steve said they actually did a research project on the commercial buildings. So he'll also send that out if people are interested. Thanks, Steve. Well, this is great. As someone who has been passionate about infiltration in commercial buildings for a long time now, it's great to see all the interest and all the interesting questions. We hope that it can go much further in terms of modeling than it is now. Can anyone, and Dan wrote, can anyone suggest resources related to maximum recommended interior relativity for cold climates? My concern is around condensation at points of exfiltration. Yeah. So if anyone can do that, that'd be great. And then Luis wants to know what Steve's email is. I don't know, Steve, if you want to put that in the chat, or you can email me. I put that earlier and I'll forward it to him for sure. Oh, there, Stephen put it there. Stephen.emmerich@nist.gov. And then someone said ISO 13788. I'm assuming that that is response to Dan's question about relative humidity in cold climates. Yeah, buildings are a beautiful thing. They're living structures that are responding to the people inside, what's going on outside, to systems. And so I think it's always an interesting topic to talk about infiltration, which can be a very big energy impact. We did a study in 2010 that said in commercial buildings, it was 6% of the energy consumed by commercial buildings is related to infiltration, and in residential buildings, 13%. So those are 2010 numbers. So it can be a big impact. Definitely it depends on where you live, where the building is located, as well as its construction and its operation. All right, well, since the questions aren't coming fast and furious anymore, I'd like to invite Nicole, who is one of the co-chairs of the ARC Simulation Committee within IBPSA USA, to give some announcements. And then we'll definitely keep the line open if people want to talk about other topics or continue talking about infiltration. So thanks again to IBPSA USA for letting me talk and have this great discussion with you all. I hope to meet you all at a future conference.
Great, thank you, Lisa, and thanks everyone for attending. This was a really exciting discussion. So like Elisa said, David and I co-chair the Architectural Simulation Subcommittee of IBPSA. It's part of the research committee. And if you are interested in things like this, helping to organize it or do further research, please reach out. We're always looking for new members. Basically, our committee organizes events, and then we also do research on various topics. And so if you have something that you're dying to research and you want a network to do that, it's a good spot for it. There's a few subcommittees as part of the research committee. And so if you go on the IBPSA website, you should be able to find it, or feel free to reach out to Lisa. She'll pass you on to me or David. So yeah, definitely all are welcome to join our meetings. We meet once a month and get to organize things like this. So I'd like to invite everyone to stay after for a little bit of social time if you want. But otherwise, thank you all for attending. It's been an exciting discussion here. And I don't know if we stop recording maybe. So
Yeah, we could stop recording, but we can stay on if anyone wants to talk about